Hello students, how are you? So today we are going to start with one of the most remarkable discoveries in the history of science, which laid the foundation of modern as well as quantum physics, and which also gained Albert Einstein his only Nobel Prize. Yes, it's an interesting fact to know that Albert Einstein didn't get a Nobel Prize for his discovery of theory of relativity. Rather, he got a Nobel Prize for photoelectric effect. And as far as your examination is concerned, this topic covers a lot of questions in NEET examination as well as in your JEE examination. So before we start with this topic, let me tell you how are we going to proceed in this topic. So we will start with the chronology, just because you may understand with this that how the things proceed on and why I am telling you that this discovery has changed the basic understanding of physics, or you can say in particular light. So it all started in 1887 with an experiment which accidentally caused Henry Hertz to discover a new concept about light. So while experimenting electromagnetic waves in 1887, Henry Hertz, you must have heard his name, the unit of frequency has been given his name. So Henry Hertz was doing an experiment about electromagnetic waves. So he discovered electromagnetic waves. During that experiment, he accidentally found a new thing. What was that thing? He found that whenever ultraviolet light incident on a metal surface, something happened and there is a spark of light. There is an electric spark of light. This was observed accidentally by Henry Hertz. He wasn't actually doing this experiment about electric spark due to ultraviolet light. He was experimenting electromagnetic waves, but accidentally he thought, or he found that whenever the UV radiation hit on a metal surface, there is an electric spark. He didn't pay much heed on that at that time. But since when the discovery of electron, which was discovered 10 years after this Henry Hertz experiment in 1897, there is one important scientist which you need to remember his name. His name was Philip Leonard. He found something very interesting. He did this experiment now deliberately, and he found that whenever there is a light of sufficient energy, now you need to pay attention from now. Whenever a light of sufficient energy hit on the metal surface, suppose this is a metal surface and this is a light of sufficient energy, or forget about sufficient energy as of now. Whenever a light hit on the metal surface, he experimented it with UV light only. Then the electrons come out of this metal surface. And when these electrons come out of the metal surface, so these electrons have some kinetic energy because they have absorbed the energy from the light, and they move, and you know, when the electron or the charged particle moves, it forms a current. So that was the reason of why the electric spark was observed when Henry Hertz was doing experiment and UV radiation fall on the metal surface, right? So this entire effect, the light incident on the metal surface, then absorbing the energy of light by the electrons, and they come out and then they begin to move with some kinetic energy, is known as photoelectric effect. Is it that simple? Or why? This is why I am telling it, but it's so interesting? No. Actually, the thing happened now. Now listen to me. Now you just tell me what will happen if I increase the intensity of this light. What should happen? So if you know the term intensity, that it is energy per unit area per unit time. So if we increase the intensity of this light, which actually Philip Leonard has done in his experiment, he thought that if intensity is increased, then the electron will absorb more energy, and when they will come out, they will have more kinetic energy. So increasing intensity will increase the kinetic energy of these electrons, and so does the current increases, because if the electron have more kinetic energy, then they will move much faster, and the rate of flow of charge or the electron is the current. So if the electrons will have more kinetic energy due to the more intensity of the incident light, then the kinetic energy would increase, and there's the photocurrent increases. So he wants to experimentally test this. See, Albert Einstein's role is not right now, so you need to be little bit patient enough to understand why I am saying this photoelectric effect is so important and so interesting as well. So you need to understand step by step how the things proceeded. Okay, So it was just a thought in the mind of Philip Leonard that when we increase the intensity of light, the kinetic energy of the electron will definitely increase because it will absorb the more energy, and so does the current will increase. So he just tried to experimentally test this thing. Is it really happening? If we increase the intensity of light, kinetic energy of the electron is increasing. So just to test this, see, first of all, you need to understand the difficulty in this testing. Why? Because electrons are so microparticles, or I shouldn't be saying that they are particles enough, because there are a lot of discoveries happened which show that electrons have dual nature, but we will not indulge into this right now. So electrons are so tiny that it is practically impossible to measure the kinetic energy. See, how you measure the kinetic energy of a moving body? Like you must have understood it mechanics from the 9th standard only. If a body of mass m is moving with certain velocity v, then what is the kinetic energy? You say, sir, half mv square. But is this formula directly applicable to electron? Is it so easy to measure the kinetic energy of the electron like this? No, because we cannot even see the electrons. The mass of the electron is very less. We can't see how many electrons are there to measure the kinetic energy. So Philip Leonard has found out an interesting and outstanding way to measure the kinetic energy of the electron. You want to know why? You want to know how? Yes. Let me tell you. He measured the kinetic energy of the electron by a negative potential called as stopping potential. I know this is going way ahead. You won't be able to understand this as of now. So let me give you an analogy. Now just me think, I have a ball in my hand and I throw it to you. See, and you need to stop this ball with your hand. So if I throw the ball slowly into your hand, so what will happen? You need to stop this ball, and if the ball is coming with slowly, that means with the less kinetic energy, you will require less energy to stop this ball. But the same ball, when thrown with a very high kinetic energy, then you need more energy to stop this ball, right? So if you cannot figure out the kinetic energy of the moving ball directly, so you can just figure out how much energy is required to stop this ball. If more energy is required to stop the ball, that directly means that the kinetic energy of the ball is high. And if the less energy is required, so it means that the kinetic energy of the body is low. So if you want to measure or just get an idea of the kinetic energy of these electrons, then you need to figure out how to stop these electrons. And Philip Leonard suggested we can stop this electron by applying a negative potential. Yes, and this negative potential is named as stopping potential, a very important term for your understanding. Let me explain you how he actually did that. So let me draw an experimental setup how he measured the kinetic energy of the electron with this negative potential. Let me see. So suppose this is our metal plate. This is our metal plate, and he incident a light or the radiation on this metal surface, and you already know that these radiation will contain some energy. The electrons in the metal will absorb that energy and they will come out of this metal plate with some kinetic energy, and we want to measure the kinetic energy of these electrons. So what Philip Leonard has done, he just kept another plate in front of this plate, and he connected these two plates with a battery of the negative potential of this battery is connected to this plate. So this plate becomes at negative potential and this plate is at positive potential. Since this plate is emitting the electron, we will call it emitter, and this plate, which is the negative potential, is collecting or stopping the electron, we call it collector. Or simply, this is my anode. You know the term anode, and this becomes our cathode. You must have heard cathode and anode in your electrochemistry. Why? Right? So the potential of this battery is denoted by V, and we are using a subscript S here, which denotes that this is the stopping potential. Now listen how the things happen. See, so when the electron will come out of this cathode or the emitter or the metal plate, the electron will rush to this plate, will try to rush with this to this plate because of the kinetic energy they have, and this plate is at negative potential, which will try to stop these electrons. See, electrons are the negative charged particles, and this negative will repel the negative, right? Or in other words, we can also say that since this is a positive plate and this is a negative plate, so there is an electric field. You must have read about it in electrostatics, that from positive to negative there will be an electric field here, right? And this electric field will apply force on this negatively charged electrons in the direction opposite to the electric field. So if the electric field is directed this way, the electron will experience a force in this direction, right? Q into E. You must have read about this topic in your electrostatics. So electron will be experiencing a force in the opposite direction. What will happen with this? This force will reduce the kinetic energy, right? And the strength of this electric field directly depends on the electric potential. The relation of electric field and electric potential, this relation you must also have studied in your electric potential chapter of class 12. You remember the relation? Yes, the relation is delta V is minus E dot D. So the greater the electric potential difference between the 2 points, the greater the electric field generated due to this potential difference, right? So more the potential, more the electric field, more the force, and electron will stop. Understood? But there is one more problem right now. What's that problem? How would you know that this electron will stop or would have stopped? How would you know? Because you cannot see the electrons, right? So how would you be confirming that electrons have actually stopped? Yes. So Philip Leonard has suggested we will actually apply we will actually connect an ammeter here, we will connect an ammeter over here. So what will happen when we apply the negative potential on this anode? This will try to stop these electrons. If the electrons would have stopped, then the reading, so electron will not be reaching this wire, so the reading of the ammeter will be 0. And if electrons would have not stopped, then this ammeter would show some reading, right? Very good. So by looking at the reading of this ammeter, we can figure out whether the electrons have stopped or not. And if the electrons have stopped, then the potential at that point when the electrons have stopped is termed as the stopping potential. Now let me show it to you how it actually been done. So suppose that this is my voltmeter which will be measuring this potential difference here, and it has some reading 1, then 2, then 3, then 4, then 5, then 6, and so on. Okay, now listen to me. Now listen to me very carefully. Suppose the light of intensity I have incidented on this metal plate. This intensity is I. The electron ejected out. They are moving with some kinetic energy, and now I am increasing the potential on the anode. So it is at 3 volt. Now when we'll increase, it will come at 4 volt, then at 5 volt, then at 6 volt. So when it is at 3 volt, we saw that there is a reading, the ammeter needle is getting deflected. What does that mean? This clearly means that at 3 volt of negative potential here, the electron didn't stop. Why didn't stop? Because the ammeter is showing the reading. That means the electron is reaching at this point. We need to stop this electron, right? Yeah. So we increase the little bit more. We increase the voltage from 3 to 4. We saw now the reading of the ammeter is slightly greater than 0. So that means 4 volt is not enough to stop the electron. We will increase a little bit more negative voltage, that is up to 4.5 volt, and now we have observed that the reading of the ammeter becomes 0. Now what does that mean? It simply means that at 4.5 negative potential of anode, there is no electron reaching here. That means all the electrons have stopped. So we can now predict the kinetic energy of the electron. What is the amount of work done by this battery to stop this electron? So you again have read this in your chapter electric potential, that work done to move a charge or to stop a charge is Q into delta V. So we are basically stopping the electron. So the work done by the battery is E. E is the charge on the electron into delta V, and delta V is nothing but the stopping potential. So what the work is done? E into Vs. This is the amount of work done to stop the electron. And if electrons have stopped, then if you have a basic understanding of mechanics, then this work done must be equal to the kinetic energy of the electron, work energy theorem. Or in simple words, suppose if a ball is coming towards me, has a kinetic energy of 100 joule, and I need to stop this ball. How much effort, how much energy do I have to put to stop this ball completely? See, To stop the ball, that means ball has a kinetic energy of 100 joule. So I need to do the work of 100 joule only, so that kinetic energy of the ball becomes 0. Right? Stopping means kinetic energy must be 0, and the ball is coming with the kinetic energy of 100 joule. So to stop that ball, we need to do the work of 100 joule. So suppose the kinetic energy of the electron is Ke, or simply K. This is the kinetic energy of the electron. To stop this electron, we need to do work which is equal to the kinetic energy of the electron, and this work is not done by you, not done by me. It is done by this battery, and the work done by the battery is E into Vs. So this is how we can figure out, by measuring the stopping potential, we can figure out the kinetic energy of the electron. Isn't it interesting? And how did we know that the electrons have stopped? By seeing the ammeter. The reading of the ammeter, when it shows 0, that simply means the electrons is completely stopped. So this was the experimental setup, how Philip Leonard is going to experimentally test whether on increasing the intensity of light, the kinetic energy of the electrons has increased or not. But before testing it, you should keep this thing in mind. What was the basic thought? If we increase the intensity, light will have more energy. It will have more energy. Electron will absorb more energy. So it will come out with a greater kinetic energy. So now let us start the experiment, that what he observed in his experiment. So we need to draw a chart. Before that, let me tell you one more thing. Suppose the electrons which are coming out here requires 4.5 volt of negative potential to stop them. So what would you say? What will the kinetic energy of the electrons? So you simply say, sir, kinetic energy is E times of 4.5. That is 4.5 electron volt. Yes, to measure the kinetic energy of the charged particle, we don't use the unit joule. We use this unit. We use this unit, electron volt, to measure the kinetic energy of the charged particle. And if you want to convert it into joule, it's very simple. Just multiply it with the charge on the electron. See, 1 electron volt is simply 1.6 into 10 to the power minus 19 joule. So if you have 4.5 volt, if 4.5 volt is required to stop this electron, that means the electrons would have kinetic energy of 4.5 electron volt. If 3 volt of potential, negative potential is required to stop the electron, then the electrons would have kinetic energy of 3 electron volt. So I am going to tell you the statement that stopping potential is the direct indicator of the kinetic energy of the electron. More the kinetic energy, more the stopping potential, right? So now just look at the experiment of Philip Leonard and what he has observed from his experiment. Okay, so let me draw a chart for you, and just keep in mind what is his thought. What he wants to tell people. He wants to check that whether increasing the intensity of light increases the kinetic energy or not. So he just draw a chart here. Let me draw a chart for you, and I'm just taking some example to showcase what actually happens when Philip Leonard has done this experiment. Okay, so let's say this is column shows the intensity of light I. This shows the stopping potential required to stop the electrons, and this is the kinetic energy, right? So let me tell you, suppose the intensity of the light in the first case, the first reading he observed at intensity I1. You can take any value, for example, like 5 watt per meter square. 5 watt per meter square. Unit of intensity, you see, intensity, the formula of intensity is power per unit area. So power has the unit watt and area is meter square. So intensity of the light incident in the first case is 5 watt per meter square. This is just an example. So he noticed that the stopping potential required to stop this electron is around, let's say, 3 volt. 3 volt is the stopping potential. That is the negative potential at a node. So tell me now, what is the kinetic energy of the electron? Yes, it's 3 electron volt. It's 3 electron volt. So now when you increase the intensity of the light, let's say the intensity is now increased I2 and the value of I2 is 10 watt per meter square. So he literally doubled the intensity of the incident radiation. So what was his thought? What he has thought, what you are thinking? That increasing intensity means more energy. More energy means electron will absorb more energy and they will come out with the more kinetic energy. And to stop this electron, you will need more stopping potential to stop them, right? But the experimental result shows the entirely different thing. You know what happened? When increasing the intensity of light, he observed that stopping potential still remains same. Yes. At 5 watt per meter square, the stopping potential was 3 volt, and at 10 watt per meter square, stopping potential was still at 3 volt. That directly indicating that the kinetic energy of the electron remains the same. Kinetic energy of electron didn't increase at all. Even if you have increased the intensity, you have Philip Leonard has repeated this experiment with other intensities as well, and in each and every experimental observation he found that whatever intensity is here, the electrons do not have increased kinetic energy, they have the same kinetic energy. That simply means, this is the point to be noted, that the intensity of light doesn't have any effect. Intensity doesn't affect kinetic energy of electrons, and so does the stopping potential. Stopping potential and kinetic energy are directly linked to each other. You see the formula? This is the formula. Kinetic energy of the electron is E times of PS. Very, very important formula, and you need to understand it, not just to learn it. You need not to mug it up. Okay, so the stopping potential doesn't increase while increasing the intensity. Why? Because the electron's kinetic energy didn't increase. But people ask, why? Why does this happen? Why do increasing intensity doesn't affect the kinetic energy of the electron? You know what happened? Philip Leonard comes out with a brilliant idea. He come out with his own hypothesis. Albert Einstein is way too far to come and jump into this effect. It's all about Philip Leonard, what he has observed. And let me tell you again, I will tell you exactly how things actually proceeded on. Then only it will make sense why this effect, photoelectric effect, is very, very interesting. And it laid the foundation of modern physics. So what was the explanation of Philip Leonard? Why doesn't the intensity affected the kinetic energy of the electron? You want to know what? Let me tell you. And this explanation is not been explained in so many books. Yes, there are some books like if you study the Resnick-Halliday part, then they have explained this hypothesis of Philip Leonard to explain this experimental observation, and this hypothesis named as trigger hypothesis. This is trigger hypothesis. In trigger hypothesis, okay, let me ask you one question. You must be celebrating Diwali every year, right? And in Diwali, there are those rockets which people love to fly, right? So let me take an example with this rocket only. Just tell me one thing, there are two rockets, rocket A and B. And if I ask you, when you lit up this rocket, you just lit up this rocket, okay? Then this rocket shoots into the sky. If I ask you, does it really affect that how you lit up this rocket, to what height or the what kinetic energy is this rocket going ahead in the sky? The answer is no. Suppose you lit up this rocket with a matchbox, with a matchstick, or you lit up this rocket with a candle, burning candle. Does it really going to affect the source of fire which you are using to lit up this rocket on with what kinetic energy is this rocket going ahead in the sky? The answer is no. Whatever source you used to lit up this rocket, the kinetic energy of the rocket with that rocket is heading in the sky depends only and only on the gunpowder which is filled in the rocket, not on the source of light or fire which you use to lit up the rocket, right? The kinetic energy of the rocket depends on the gunpowder, the material. The height of the rocket gained, it depends again on the gunpowder. It doesn't have any relation to the source of fire which you have used to light up this rocket. So there are two rockets. This is a bigger rocket, so it has more gunpowder into it. So even if you light up the rocket with the two different sources. If it has a matchbox and if it has a candle, the rocket will that rocket will achieve more height, the more kinetic energy, which has more gunpowder, not the source of fire. So what actually is this fire doing here? This fire is just triggering out some reactions into the rocket. So the gunpowder is burning and then it starts going ahead with some kinetic energy, right? So this source of fire is just having a trigger effect. It's just triggering the reactions. And Philip Leonard explained this is exactly what light is doing with the metal plate. So whenever the light is hitting the metal surface, it actually doesn't have any relation whatsoever with the kinetic energy of the electrons which are emitting out. Light is just triggering, just like this source of fire is triggering the reactions into the rocket, light is also just triggering some sort of reactions into the metal surface. And the kinetic energy of the ejected electron doesn't have any relation whatsoever with the source of light. So the kinetic energy didn't change while you changed the intensity of light, because if you change the source of fire, it didn't have any effect on the kinetic energy of the rocket. So similarly, you change the intensity of light, it doesn't have any effect on the kinetic energy of the electron, because light is just triggering the reactions into the metal surface. Is this explanation true as per now? The answer is no. This hypothesis, this trigger hypothesis failed, and it failed miserably. But as of then, when he explained, because he wanted to explain his experimental results, because he experimented that by changing the intensity, there is no effect on the kinetic energy of the electron. So he wants to prove why is this happening. So he just given out his own hypothesis. He said that because light doesn't have any effect on the kinetic energy of the electron, it is just triggering out of the reaction in the metal plate. Okay, so the kinetic energy of the electron is entirely the property of the metal only. Yes, this was the explanation given by the Philip Leonard in trigger hypothesis. But you know this is not true. But why and when does this experiment fail? Philip Leonard has himself discarded his own hypothesis by doing one more experiment. He experimented the same thing. Same again. Now, let me draw the quick setup again. This is our metal plate, which is the cathode. Okay. So, this metal plate is hit by a light source. This is the stopping potential. We are going to measure the stopping potential. Now, he did the same experiment with different frequencies of light. He just want to prove that light doesn't have any effect on the kinetic energy of the electron. It is just triggering. So if light is just triggering, so it should not depend on the frequency of light as well, right? So whether we are using the red color light or some different color of light, let's say yellow or a blue color light, it should not have any effect either, right? And you already know that different color of light means different frequency. You must have understand about Vibgyor. Violet has the highest frequency and red has the lowest frequency, right? Ultraviolet has frequency even higher than the violet. That's why its name comes ultraviolet. So when the frequency of light is changed, it shouldn't have any effect on the kinetic energy of the electron. He again wants to test this experimentally. So this time in his chart, he just changed the frequency of the light. And you know what he observed? He observed that this time when the light of higher frequency, let's say a blue light and an example of, I take an example of red light. So when a light of higher frequency, that is blue or ultraviolet light, okay, hit on the metal surface, then if the stopping potential is, let's say 5 volt, example, this is just an example. If the light of blue color hit on the metal surface, then the stopping potential is 5 volt. And if the stopping potential is 5 volt, that clearly means that the kinetic energy is 5 electron volt, right? And if the lower frequency, let's say red color light hits on the metal surface, I'm just taking it for example, red frequency of red is lower than the frequency of blue. then the stopping potential and kinetic energy both decreases. So if the frequency decreases, the kinetic energy decreases. And how are we concluding that kinetic energy decreases? Because we have seen that stopping potential decreases. Stopping potential decreases. Stopping potential, the negative potential on the anode which requires to stop this electron, and how the electron have stopped or not, how are we going to figure it out? By seeing this ammeter reading. I have just explained. I hope you are understanding what I am trying to say, and you are taking interest into it. So when he changed the frequency of light, he saw that the stopping potential now changed. Higher frequency needs higher stopping potential to stop the electron. That means the kinetic energy of the electron which are emitting out of the metal surface has higher kinetic energy. Is it clear to you all or not? So this way trigger hypothesis failed, because trigger hypothesis says that light is just triggering the reactions in the metal surface. It doesn't have any effect whatsoever in the kinetic energy of the electron. It does have effect. Although its intensity of light is not affecting the kinetic energy, but the frequency of light does affect the kinetic energy of the electron. And here Philip Leonard failed to explain further. He couldn't explain now why is this actually happening, why intensity is not affecting and why the frequency of light is affecting. I hope this makes sense to you. And by this now you must have understood 3-4 major points. That light of sufficient energy or frequency emits the electron. You must have understood the meaning of stopping potential. Literally you must have felt what actually stopping potential is, how you measure the kinetic energy of the electrons, and what were the experimental observation, or in other words, how is the dependency of kinetic energy on intensity and frequency. Kinetic energy of the electrons, photoelectrons, doesn't depend on the intensity of the light, but it does depend on the frequency. Although Philip Leonard's trigger hypothesis can't explain this experimental observation, because trigger hypothesis is failed, it just said that light is triggering out the reactions. So Philip Leonard can't explain this. Now comes the entry of, can you have any guess? Okay, I can hear Albert Einstein. No, not right. You need to be a little bit more patient for the entry of your final hero. Before Albert Einstein, there was something more happening in the world, which was even more interesting. There is a scientist, and you must have heard his name, very great and genius scientist named as Max Planck. He was studying about the black body radiation at that time, and when Philip Leonard was doing all this, and according to Max Planck's theory, he explained some unique feature of light, very unique feature of light. So Max Planck jumps in here in this story of light, and he also given some beautiful fact about some very interesting fact which we called as quantization of energy. A beautiful phenomenon, purely out of the box thinking of Max Planck. Quantization of energy. He gave the quantization of energy, but there is at one point Max Planck also failed. He also didn't have an idea something which was happening really interesting, and then to connect the dots of Philip Leonard's experiment, why is this happening, and Max Planck's theory of quantization of energy, final hero Albert Einstein came. He connects all the dots, given a beautiful different theory. He has changed the complete perception of light of the people at that time, and then came the theory of photoelectric effect. So this was the first fundamental lecture about how the things proceeded in the discovery of photoelectric effects. So let me tell you, in the next lecture we are going to tell what Max Planck has to say about quantization of energy and how did he explain quantization of energy, and then how Albert Einstein came and he solved the puzzle of Philip Leonard as well as Max Planck, which eventually earned him a Nobel Prize. So in the next lecture we are going to see this thing. So thank you. I hope